Drop a fish into a river and watch it climb straight up the leg of a wading horse, releasing a jolt strong enough to buckle the animal's knees. One of these creatures unloads 800 volts, several times the force of the socket behind your couch, and it can do it in open air. For centuries, we filed it under one lazy label: a single sluggish species, a living wire that shocks by reflex and nothing more. Cameras and DNA say otherwise. So why does a so-called simple fish leap, aim, and strike like a hunter? The answer rewrites everything. Start with the name, because the name is where the trouble begins. The electric eel isn't an eel. Despite the shape, long and bare and gliding through the tea-colored water of the Amazon, it belongs to a group called the naked-back nifishes. And its nearest relatives are catfish and carp, not the eels most people picture. Naturalists first pinned a Latin name on it back in 1766, and for the next 2.5 centuries, the story barely moved. One animal, one species. A river curiosity that could deliver a nasty jolt to anyone careless enough to wade in. Generations of textbooks printed more or less the same paragraph, and that paragraph was wrong in more ways than anyone suspected. To see why the errors matter, you have to look under the skin. Cut into an electric eel, and you find that the fish is mostly power supply. Around 4/5 of its body length is given over to electric organs. 3 of them, packed one behind the other. Inside sit thousands of flat, disc-shaped cells called electrocytes, stacked in long columns like coins in a rolled tube. Each cell produces only a faint charge on its own. Wired in series and fired at the same instant, they add up exactly the way cells add up inside a battery. That's not a loose comparison. The underlying physics really is battery physics, which is precisely why the living battery label stuck so hard and did so much quiet damage to how people imagined the animal. The firing itself is where you first sense that something more deliberate is going on. The eel doesn't leak voltage at random. A command from its nervous system reaches those stacked cells, and ion channels snap open across each one almost simultaneously, letting sodium flood in and flipping thousands of tiny charges into a single coordinated pulse. Timing is everything. If the cells fired out of step, the voltages wouldn't stack, and the shock would fizzle. The eel controls that synchrony down to fractions of a millisecond, and it can choose between a gentle trickle of pulses and a full knockout volley. A dumb battery has one setting. This animal has a dial and a finger on it. Then, in 2019, the whole tidy picture came apart. A team led by the biologist C. David de Santana worked through museum specimens and fresh collections across the Amazon and showed that the one species everyone had accepted since 1766 was actually at least 3, separated by genetics and geography, hiding in plain sight inside one of the most studied, shocking animals on Earth. One of the newly named species, Electrophorus volti, did something none of them expected. In testing, it discharged 860 volts. The previous ceiling for any electric eel, and for any living thing measured, had been somewhere around 650. A famous fish had been concealing a world record. Why would one species climb so much higher than the rest? The leading explanation ties the voltage to the water itself. Electrophorus volti tends to live in the clearer, faster streams of the Brazilian highlands, where the water carries fewer dissolved minerals and therefore conducts electricity more poorly than the murky lowland rivers. Push a current through more resistant water, and more of it is lost along the way. So a highland eel that needs to reach prey or fend off a threat may have been pushed by evolution to generate a stronger jolt just to land the same punch. It's a hypothesis, not a settled fact, but it fits the pattern, and it reframes the record voltage as an answer to an environmental problem rather than a party trick. Sit with what that discovery implies. If a fish this famous could hide 2 entire species and a record-breaking shock until 2019, then the confident textbook paragraph wasn't merely incomplete. It was resting on almost nothing. And the closer researchers looked, the stranger the animal became, because voltage turned out to be the least interesting thing about it. The obvious assumption is that the shock is the whole game. The eel swims up on a school of fish, unloads one massive volley, and swallows whatever floats up stunned. That does happen. A high voltage discharge genuinely stuns nearby prey. If that were the end of the story, it would be simple and a little boring. Strong fish, big jolt, dinner. But the Amazon the eel actually lives in is dark, silty, and cluttered with roots and debris. Prey hides. A blind blast into muddy water is expensive because those discharges cost real energy, and it does nothing about a small fish sitting frozen behind a tangle where the eel can't see it. So the sharper question isn't how hard the eel can hit, it's how it finds anything to hit at all. The answer is that it barely uses its eyes. Alongside the big knockout organ, the eel runs a second, far weaker electrical system, ticking out low voltage pulses that spread through the water around its body. When those pulses meet anything that conducts differently from water, a fish, a stone, a submerged branch, the field bends, and receptors in the eel's skin read the distortion. The animal builds a map of its surroundings out of electricity instead of light. In black water, where vision is close to useless, that is a devastating edge. It also deepens the puzzle, because a perfectly motionless fish still barely disturbs the field. Something has to force that hidden prey to give itself away. This is where the battery idea dies for good. In a series of experiments at Vanderbilt University, the neuroscientist Kenneth Catania showed that an electric eel doesn't only shock its prey, it hijacks the prey's body. Just before the killing volley, the eel fires pairs of quick, precisely spaced pulses. Those pulses skip past the target's brain and activate its motor nerves directly, forcing the muscles to contract whether the animal wants them to or not. A fish that was holding dead still suddenly twitches, an involuntary spasm it can't suppress, and in that flash, it reveals exactly where it is. The eel has effectively found a remote control for another creature's muscles, then delivers the full discharge to prey it made move. It can also turn the shock up. A struggling fish, or one big enough to fight back, gets different handling. Catania documented the eel curling into a tight C, pulling the 2 ends of its electric organ, the positive and negative poles of that living battery, toward each other with the prey trapped in the middle. Bringing the poles closer concentrates the field between them, and the strength of the shock on the pinned animal more than doubles. It's the electrical equivalent of folding a stun weapon around a target, so both contacts press into the same spot. None of this reads as blind reflex. It reads as an animal fitting its attack to the specific problem in front of it. Even the eel's defense turned out to break the rules once someone filmed it properly. Around 1800, the explorer Alexander von Humboldt described Venezuelan fishermen driving horses into a pool to wear the eels out, and wrote of eels rearing up against the horses in a thrashing. Shocking melee, with some of the horses stunned and drowned. For generations, that account was filed under tall tale, colourful nonsense from a colourful age. In 2016, Catania caught the real behaviour on camera. Cornered and threatened, an electric eel will throw part of its body clear of the water, press its chin against the intruder, and climb higher up its side while discharging. Staying submerged would let the current bleed away through the whole pool. By leaving the water and touching the target directly, the eel turns itself into a battery whose circuit runs straight through the threat, and the shock lands with far more force. Humboldt hadn't exaggerated. He'd seen something we spent 2 centuries refusing to believe. By now, the picture has already inverted. Not a passive tube of stored voltage, but a sensing, calculating hunter that maps the dark in electric pulses, puppeteers its prey into revealing itself, amplifies its own shock on demand, and launches out of its element to defend itself. Yet all of that still rested on one quiet assumption everyone shared, scientists included. They assumed the eel did every bit of it alone. There was a hint hiding in the eel's own signals. Those low-voltage pulses aren't only for feeling out the world. These knifefish also read one another's electric fields, sensing when another of their kind is near, and, in some cases, exchanging information through the rhythm of their discharges. In other words, an electric eel already carries the equipment to know that other eels are around it. For a long time, nobody thought that mattered much, because these animals were, by definition, loners. That definition was about to fail. It failed in 2021. De Santana was back in the Amazon, at a small lake fed by the Iriri River in the Brazilian state of Pará, when he saw something he said had never been documented in electric eels. More than 100 adult eels were gathered in the same stretch of water. Animals that were supposed to be strictly solitary were packed together by the dozen. His group had first glimpsed the scene in 2012, returned in 2014 to confirm it, and what they described knocked over one of the last standing assumptions about the species. These eels were hunting as a group. Coordinated group hunting is ordinary among mammals, but it is genuinely rare in fish, and no one had ever recorded these animals doing it. And it wasn't a chaotic mob feeding. There was structure to it. The large assembly would drive shoals of small fish, tetras only an inch or two long, herding them into tighter and tighter formations until the prey were crushed into a dense ball near the surface. Then smaller bands, sometimes just a handful of eels, would separate from the main group, slide in close, and fire together. The joint discharges struck the prey ball in the same instant. Stunned tetras were flung right out of the water and rained back down where the eels snapped them up. No single eel needs 800 volts to kill a fish the size of your thumb, but a synchronized volley from a coordinated band turns an entire shoal into an easy harvest in seconds. The teamwork, not the raw power, is what makes it deadly. Here's the part honest science makes you say plainly. This astonishing behavior has been documented in one species, at essentially one location, under particular conditions. A dry season lake where dropping water levels concentrated both the eels and their food. We don't yet know how the eels coordinate, whether it's true cooperation or many individuals cashing in on the same lucky pileup, or how common it is across the wider basin. It might turn out to be widespread. It might turn out to be a rare product of geography and season. What we can say is that the whole discovery sits on a thin stack of observations in a region we are actively clearing. The same rivers where this unfolded face deforestation and habitat loss, which means populations and behaviors, could vanish before anyone even describes them. So step back to the question we started with. What did we actually get wrong about the electric eel? The easy answer was never entirely false. It is powerful. It is built like a battery, and one of its species really can fire the highest voltage ever measured in a living thing. But power was the part we could put a number on. So power was the part we fixed our attention on, and it turned out to be the shallowest thing about the fish. The real animal finds hidden prey with a self-made electric field, forces that prey to betray itself by seizing its muscles, folds its body to double its own shock, throws itself out of the water to strike at a threat, and, in at least one place, works with others to farm whole schools. It isn't a battery that happens to be alive. It's a precision electrical predator, and the 860 volts are just its loudest tool. Which brings us back to the surface of the water. That's the detail that keeps returning here. The boundary the eel was never supposed to cross. Then, the plane it erupts through to shock a horse, then the churning ring where 100 hunters drive their prey into a ball. Look at a stretch of still Amazon backwater now, and it reads differently. Somewhere under that flat brown skin, there may be an eel sketching the dark in pulses you'll never feel, or a species no one has named yet, or a behavior we simply haven't been lucky enough to film. We spent 250 years certain we understood this animal. Nearly everything we actually know about it, we learned in the last 10. The surface still hasn't shown us what's underneath,